This AP problem from the AP Level C exam from the year 2011, I believe this is problem number 3, provides good practice in applying Amperes Law. So we're shown a conductor that's hollowed out, and it has an inner radius of A and an outer radius of B, and we have to answer a question that says, derive an expression for the magnetic field in the following regions, where R is less than A. So in other words, what's the magnetic field at any point inside that shaded area? Then we have to figure out what's the magnetic field in this shaded area. And then lastly, what's the magnetic field at some point outside of this whole conductor? Okay, so using Amperes Law, let's do the first part. Amperes Law says the integral of B dot ds is equal to mu naught times I enclosed. To use Amperes Law, we have to picture an Amperian loop. So I'm going to picture a little loop in the form of a circle somewhere in here, and the radius of my Amperian loop is less than A, just like we're being asked. So the one thing about making my Amperian loop in a circle is if there is any magnetic field, I'm pretty sure that the left side of the equation is just going to simplify to B times 2 pi r. But the right side, here's the trick to it, how much current is enclosed by that Amperian loop? Well, there is no current in this region. All of the current lies within the solid part of the conductor. So because the whole right side of the equation is 0, then that means B is equal to 0 in that region. That was easy. Okay, so now let's find the magnetic field at some point here. Again, we have to do it using Amperes Law. So let's draw an Amperian loop. I guess I'd draw a circle whose radius is less than B but greater than A. So the whole left side of the equation, B dot ds, is just going to become B times the integral of ds, and that's equal to mu naught times the amount of current enclosed. Or we could say this is the integral of j dA. The total path length of my Amperian loop is just the circumference of a circle. So this is B times 2 pi r equals mu naught. Let's read the problem carefully. Oh yeah, it's got a uniform current density. So I can take this j out of the integral, and then I have the integral of dA. All right. So B times 2 pi r is equal to mu naught times j. What is the current density? So we're told that this conductor carries a current of I. Current density is the total current divided by the total area. So let's see, what's the total area of this conductor? I guess it's equal to pi b squared minus pi a squared, right? So in other words, I can substitute in place of j, I divided by pi times the quantity b squared minus a squared. And then dA is 2 pi r dr, but careful here, I only need to account for any current density. Well, there is no current density from 0 up to A. There's only current density from A up to B, but my Amperian loop only extends out to R. So to account for the amount of current that's enclosed, I need to account for current starting from R equals A and only going up to R equals R. Okay, so the integral of 2 pi r dr from A to R. Let's cancel out that 2 with that 2 and this pi with this pi. So we have B equals mu naught I divided by pi b squared minus a squared, don't forget this r, times the integral of r dr from a to r. Now this comes out to 1/2 r squared evaluated from a to r, which is 1/2 r squared minus a squared. So we find that b is equal to mu naught I times r squared minus a squared divided by 2r times the quantity b squared minus a squared. Now let's check. I think that's our final answer for this question, and I want to check something here. What if we had the case where r equals b? In other words, we're trying to find the magnetic field, not so much somewhere in between a and b, but right at the surface, just before we get to points outside. Well, if that's the case, then we get b equals mu naught I times b squared minus a squared divided by 2r times b squared minus a squared, so that cancels out, and we get mu naught I over 2, oh, I caught my mistake. I forgot this pi. So that would be here. And so we get the result that we expect. B equals mu naught I over 2 pi r. Okay. So let's put the answer here. B equals mu naught I times r squared minus a squared divided by 2 pi times b squared minus a squared. Let's do the last part. Find the magnetic field at a point outside of the whole conductor. I think this is going to be a bit easier. So there's my hollow conductor. There's a point somewhere outside of it. So I make an Amperian loop that passes through that point. And we say that the integral of b dot ds is equal to mu naught times I enclosed. We know this is going to be, but that's a, that's b, and that's lowercase r. So the whole left side of our calculation is just going to become b times 2 pi r equals mu naught. Now, what's the I enclosed? Well, there's no current enclosed in this region of space, none here, but the current that passes through here is just all of the current. So the I enclosed is capital I. So we get b equals mu naught I over 2 pi r. B equals mu naught I over 2 pi r, just as we expect. Indicate the direction of the field at that point P. Well, we just have to use the right-hand rule. They're telling us that the current flows in this direction, so when the eyeball looks down the axis, we see it like this. So the current is flowing into the page as stated here. So if you point your thumb into the page, then you see the magnetic field that passes through point P represents a circular magnetic field line that goes around in a clockwise direction. So they say indicate on the diagram above. We could also say it in words that it's clockwise. So at point P, it points down and to the right. An electron is at rest at point P. Describe any electromagnetic force acting on the electron. Well, the key here is that the electron is at rest, and when it comes to magnetic forces, magnetic fields only exert force on moving charge, so force equals 0. End of story.